Alright, we're doing Johnson's algorithm. In Johnson's algorithm is an algorithm for the all pairs problem where the weights can be arbitrary, they're allowed to be negative. And of course, like all shortest path problems, there may be no negative cycles. However, we're allowed to have negative edges. Now, the way the algorithm works is that all the weights are adjusted, and we want to adjust them in such a way that the weight of every edge, represented by the red number, is non-negative. For example, if we have this edge and this edge here, P and Q are the weights, and if the vertices T, U, and V have adjustment terms X, Y, and Z, we add X and subtract Y from the weight of the edge from T to U, and then here we add Y and subtract Z from this weight, and then of course if there is an edge here we add X and subtract Z. Now the reason that this works is we get the same shortest paths, just not the same weights, because this path is shorter than that one if and only if the sum of the two black weights is less than that R. But the new red weights, this sum is also less than that. So this P plus Q is less than R if and only if these adjusted weights are less than this adjusted weight. And you can see that right away because the Y's cancel. So that's the basic idea. The basic idea is to get an adjustment term for every node, but not just any old adjustment term. We have to ensure that the new weights, which represented here in red, are never negative. And because there are no negative cycles, it is always possible to do that. All right, now the way that is done is to create a new graph with a new source vertex S and solve the single source problem on that graph. Now this new directed graph, which has weights on it, the same as the old one, but the new edges all have weight 0. Now, we then solve the single source problem, and we label each vertex by the weight of the shortest path from S to that vertex. And that shortest path includes both the zeros, it also includes the positive or negative terms inside. Now, for example, in this particular case, the shortest path from S to B has weight 0 because that path is the shortest one. The shortest path to C has weight -2. The weights of these shortest paths are never more than 0, and the reason is because 0 is always there is always a path of length 0, of weight 0. So it could be that the shortest one has smaller than 0 weight. For example, to S to B, then B to C has weight -2. And -3 is the shortest, is the smallest weight of any path from S to A. And that would go B, C, A. And we can fill out the rest of these. This shortest weight would be -5. And how would we do that? That would go to B, C, E, and then B, C, E, D would have weight -3, even though the last edge there is positive. Now, using those weights, we adjust all of the edge weights. All right, so let's go through that adjustment here. When we have an edge from T to U, we adjust by adding one term and subtracting another. For example, here, from C to E, pause. The weight is -3. What we do is we add -2 and subtract -5. All right, for example, in the edge from C to E, here I have to add -3, add -2 and subtract -5. That gives it the weight 0. All right, now from B to C, I add 0, take -2, add 0, subtract -2, which also gives me 0. For the weight of the edge from C to A, I take -1, and then I have to add -2 and subtract -3, which also gives me 0. Now, from C to D, I take the 4, and I add -2 and subtract -3, which means that the actual value here is 5. 4 plus -2 is 2. Subtract -3 gives you +5. Now, from here, E to D, I have 2 plus -5 is -3. Subtract -3 gives you 0. All right, let's look at this one. D, add -3 and subtract 0, that gives you +1. And here, A to B, add -3 to 4 and subtract 0 gives you a +1. All right, now then there's this long edge here, which is weight 6. Add -5 and subtract 3, so that gives you a weight of 4. Now, the graph with the new red weights has no negative weights. And then, what we do is we apply Dijkstra's algorithm once for each node. Thus we solve the single source problem n times, one for each vertex. Now, to solve Dijkstra's algorithm takes m log n time. We do it n times, so the complexity is nm log n. Now that means that Johnson's algorithm is not better than Floyd-Warshall unless m is fairly small, substantially less than m squared. And since I said most graphs are actually sparse, then that is actually a typical situation. Now, what happens here when we solve this, we're going to create a back pointer matrix.